So we can describe heat changes through a process called enthalpy. We would represent that through a delta H or a Q as our variable. And delta H, remember the delta symbol means the change in, and H of course stands for heat. So the change in heat is going to be our enthalpy. If we have an exothermic reaction, this is going to be characterized by having a negative delta H. And that's something that's very important to remember. So that also means that heat is going to be lost during my reaction, or heat is going to be released during my reaction. So we can show that right here, that if I have a reaction within this Erlenmeyer flask, energy is going to be given off during the reaction. So since energy is given off, it's going to cause the temperature to rise, or the temperature is going to go up. So if energy is given off, if temperature goes up, or if we have a negative delta H, I know that I have an exothermic reaction. If I have an endothermic reaction, on the other hand, I know that I'm going to have a positive delta H, or my net energy is going to be a positive number. That means that heat is gained in the process. Okay, I've taken in heat. I've taken heat into my reaction. So if my reaction is taking place inside this Erlenmeyer flask, I show that Q is entering the system, and it's so since it's taking energy from the environment, that means that it's going to cause the temperature of the environment to drop. So we would feel an endothermic reaction as getting colder. So if we take a look at this chart, it's going to help us summarize what we know about endothermic and exothermic reactions. Okay, an endothermic reaction is going to mean that energy is required, meaning that we're going to take energy into the system. When we take that energy into the system, we would observe the temperature going down. Okay, the temperature is going to drop. Very, very important to understand that it's going to give you a positive delta H. Okay, meaning that your energy consumption, or your energy is going to be a higher number. It's going to be a positive number. We would show that in a reaction by showing that the heat, or that the energy, is on the reactant's side of my reaction. That means that I have to take energy in with my reactants in order to form a product. If we were to show that graphically, remember, anytime that we have a change, we're always going to do the final whatever minus the initial whatever. Okay, so same thing here. I'm going to do the final energy minus the initial energy to get my delta H. Well, if my final energy is higher than my initial energy, then that delta H is going to be a positive number. Here's my positive right here. So that's how I know that this graph, okay, if I have a situation which looks like this, it's going to be an endothermic reaction. Uh, to summarize an exothermic reaction, it's going to be basically all the opposites of this. I know that energy is going to be released. The temperature of my surroundings is going to increase. My delta H, very important to remember the delta H. If I have a negative delta H, that tells me that it's exothermic. Okay, I would highlight this in your notes. Okay, highlight this and highlight this. It's very important to understand that negative delta H is exothermic, positive delta H is endothermic. Okay, I'm going to write this graphically by showing that, or excuse me, not graphically, in a reaction, I'm going to show that heat is on the product side, meaning that heat was a product of my reaction. Heat was released after the reaction, or during the reaction. Okay. I can also show this graphically by saying that my energy is lower than I started. Okay, so my final energy is lower than my initial energy. So then when I do my delta H formula, final energy minus initial energy, my delta H is going to be a negative number. So since it's negative, I also know that it's going to be